Yeah, like, you can pass through hedges. You're a really terribly rude pizza delivery man. But what else? Yeah? Yeah, well, no, you can set it up so k is the x-axis. That's a great thing how to set it up, absolutely. But in terms of the placement of these houses, does the question say anything about how far the houses are from the road?
No.
What do you really kind of have to assume about the distance the houses are from the road? They're the same distance. Can you make this question arbitrarily weird if, like, one house is 6 inches from the road and the other one is like 60 miles from the road?
Yeah.
Yeah, that would not really make this a consistent question. But if we assume both houses are the same distance from the road, we can actually summarize this. We have H, we have J, which I'll move up a little, and we have K. Do you agree with that?
Mm-hmm.
And what do we know? This is going to be on could be the x-axis. If we want to put K on the x-axis, what could H be on? The y-axis, sure. And what are we assuming about? We're assuming that this value right here is the same y value all the way across. So what's the path of this person? The person goes on HK twice and goes on JK once. Do you agree with that? So is everybody okay with the setup of this question? Is everybody okay with the setup of this question? Do you understand what it's asking? It's asking, explain how to estimate k so that the distance you travel is as small as possible. It's as small as possible. So which path are you traveling on twice? HK. So theoretically, do we want that path to be shorter or longer than JK? It might be better if it's short because you're spending more time on it. Luke.
Can I ask if K was halfway between?
We don't know. That's what we're trying to figure out. We're trying to find out where is K going to be to minimize this overall distance. So that's the distance from H to K. So what would we want to find out next? The distance from J to K, exactly. The distance from J to K is going to be the square root of, what's the horizontal distance? Nope. The bigger number is 8 or the bigger number is x? 8 minus x, thank you, is the horizontal distance. Good. And what's the vertical distance? Yeah, 4 minus 0 again. Does everybody see where those numbers are coming from?
Mm-hmm.
Okay, so what is JK going to be, the distance? The square root of what? Yeah, you can multiply it out or you can just do this, plus 16. So if we want to figure out the total distance this person walks, what is based on those equations, what's the total distance? Total distance walked. Do you even know what kind of function that is?
Yeah, it's a
No? Really? Yes, it's curvy. Congratulations. Yes, it is curvy. Yes. Is that a quadratic function? Is that a linear function? Oh, you struck out. Those are the only functions you've really worked with so far. Maybe cubics a little bit. Have you really dealt with anything in detail, any other functions? No. In AP Calculus, you would be able to find the minimum value of this function using math that you have not even begun to learn about. So this actually models the total distance walked, but would we be able to solve this by hand? No. What could you use to solve this if you wanted to? Your calculator. You're absolutely right. Your calculator. A parallelogram, can you really do anything with it? Not really. Okay, in a parallelogram, what do you know about opposite angles? Congruent. So you know that D is going to be equal to B plus 10. And you also know that C is equal to B minus 10. Right. What else do you know about a parallelogram? Consecutive angles are? Consecutive angles are? I can't hear you.
Complementary.
What does complementary mean?
They add up to equal 90.
Does this look like?
I mean, yeah.
So that plus that is going to be what?
180.
180. Right. So therefore, what else can we set up? We know that D plus B minus 10 is equal to
180.
180. We also know that B plus 10 plus C is equal to 180. We also know that D plus C is equal to 180. And we know that b minus 10 plus b plus 10 is equal to 180. So those are all the equations we can write. Is that way more information than we need?
Yes.
I liked writing them all out because I just wanted to do this. That cancels there, and you end up with 2b equals 180. So what's b equal? 90. Now can you collapse all these out? So what does d equal? So 100. And what does c? B plus 10.
Oh, yeah.
100. No, it's fine. It's fine. What does c equal?
80.
80. And that's all we need, right?
Yeah.
See how that works? There's so many relationships that you can come up. Is that more information than we need?
Yes.
Yeah, you didn't have to use all of them, actually. I just wrote them out until I got, hey, that one's nice. Is that the nicest one to deal with?
Yeah.
We didn't even actually have to substitute any variables in this case. It just kind of fell together. Perpendicular. Let me finish this drawing. What are those lines called individually? They're called diagonals. What do the diagonals of a parallelogram do to each other? They definitely bisect each other. They're not necessarily, they're only perpendicular if it's a regular, or it's wrong, yeah, a regular polygon, exactly. But we do know that they bisect each other. So if that's the case, you know that 2f minus 5 has to be what? 5f minus 17. How many equations is that? How many variables is that? 1. So what do you end up with? I don't know. 12 is equal to 3f. So what does f equal?
4.
4. And then what's the second one? F plus 2 is equal to g. So g is equal to 6. Yeah. Does that make sense?
Yes.
They definitely bisect each other. Are they definitely perpendicular? Not necessarily. Not necessarily. Only if it's regular. Okay, we'll do a couple. 39 says, find a point C on the x-axis so that AC plus BC is a minimum. So what would be a good way to start this question? If we're doing, well, what should we do first before we do anything? What would be a good thing to do? What? Plot them. Let's plot these points. So we have negative 1, 4, which is going to be right here. There's A. And B is 6, 3. Right there, is that correct? Yeah. 6, 3, and negative 1, 4. And where's point C?
On the x-axis.
On the x-axis. Does this look remarkably like the question we just did? Yeah, so let's actually finish this one, and then it'll help you on the other one. So C is somewhere. Do we have any idea what the x value for C is?
Nope.
Let's not call it x. Let's call it something else. What's a good letter?
N.
Sure, C. C, comma, 0. Yeah, or 6 minus C. Doesn't matter which way, right? We've already determined. Plus what? Exactly. Good. So what does this equal? 6 minus C squared plus 9. And what are we trying to do? We're trying to minimize. We want to minimize AC plus BC. Do we have any way of doing that algebraically yet? No, I pretty emphatically said there's no way for you to do that algebraically, but what could you use? So what do you want to graph? F of x is equal to what? Yeah, we want to graph, but instead of saying C, does it matter what we call the variable? It does not, right. So we have, how about x plus 1 squared plus 16 plus what? Plus 9. There you go. Nice. Okay, so we're trying to minimize that function. So if we're going to minimize that function and use our calculators, what are we going to have to do first on our calculators? What? Set the window of what? So what are we doing? You're baking it cookies? What are you trying to do? You're taking this function and what are you doing with it? Coloring it orange? What's the lowest value C could reasonably be expected to be? What's the smallest value? You can't go farther left? C can go anywhere left or right on the x-axis, right? Yeah, maybe. It doesn't seem likely that it would be left of negative 1, does it? What about what's the farthest to the right it's going to go?
7.
Yeah, so you could say the domain of this function is x is less than or equal to 6, but it's greater than or equal to -1. So let's look at our graph again. From -1 to 6, does it go down a little bit? Does the area go down? Does the distance go down?
Yeah.
Yeah. On your calculator, see up here it says calc above trace right there? Calc, it's above trace. You hit second trace. And which one do you think I'm going to choose? Put the calculators down. Which one am I going to choose? Minimum 3. It's asking for something to the left of the minimum, and then you hit enter. And then what's it ask you for? To the right of it, and you hit enter. And then what's it ask you for? A guess. I'm going to guess right about here and go enter. It thinks for a second and goes, boom. Look at that. What does this tell us? What does this tell us? We just found the minimum value. So this right here is the x value. That right there is the y value, the output. The input was the x value. What was the output here? We were modeling y, which was what? Distance. Distance. So what is the minimum distance to 3 decimal places? Speak louder.
9.89.
9.899. Where is the minimum when x is what? When the calculator says 2.999999989, what can you pretty much assume it is? Yeah. Exactly. Your calculator, depending on how far you zoomed in, sometimes will tell you a slightly different answer. Because is it doing an exact thing here? No, it's estimating. Your calculator is estimating to 10 decimal places. And depending on how far you zoom in, it might be a little different. But either way, it's pretty safe to assume that this minimum occurs when x is equal to 3. When x is equal to 3. Exactly. So if this question asks what is the minimum distance, what's the answer to that? What is the minimum distance? I can't hear you.
9.899.
Yes. Where does it occur? Yes. So be careful. One of the saddest things I see is the question will ask, what's the distance? And then someone will say 3. Is that correct? No, that is not correct. If I were to draw A to P, we know that's the same distance. That's the same distance as this. What type of shape did I draw? What is PBB? What is this shape right there?
Polygon.
It is a polygon. That is correct. What type of polygon? It is a parallelogram. And what do we know about the diagonals of a parallelogram? They bisect each other. Not only this, this is an equilateral parallelogram. And Missy, what do we know about equilateral parallelograms? Bisectors, right? So now what do we know then? We know that if that's the intersection point right there, we know that this distance is the same as that distance. So I'd like you to practice this right now. Practice reflecting a point across a line. I would like you to do this. So everybody put your pencils down, stop drawing for a second, everybody just watch. Here is your piece of paper. This is what I'd like you to do. You're going to draw, you can use half of one if you'd like. You're going to draw a triangle. A, B, C. And then you're going to pick a point, P. This is what I'd like you to do. You're going to rotate triangle ABC around P a certain number of degrees. And by certain number of degrees, you get to pick. So how many degrees do you want to go?
180.
Nah. Let's go to 30 degrees. What I mean by that is, if you were to take the board and put a tack in P, and then rotate the whole board, and we'll say which direction. Let's go counterclockwise. So that's spinning to the left. If I were to go tack the board here, and then take this and rotate it, how would you do that? Do you understand what I'm saying?
Yes.
How would you rotate this shape 30 degrees counterclockwise around the point P?